Welcome to this fascinating journey into the evolution of terrestrial ectotherms. Imagine spending your entire life floating in a warm, supportive pool, only to be suddenly tossed onto cold, hard concrete. That harsh reality is exactly what the first aquatic vertebrates faced millions of years ago. Today, we will explore the incredible biological and physical adaptations that allowed these pioneering creatures to survive, thrive, and eventually pave the way for all land-dwelling animals, including us. To truly appreciate this evolutionary leap, we must travel back 360 to 400 million years to the Devonian period. This transition from water to land was not just a change of scenery, it was a monumental physical challenge. Early pioneers, known as lobe-finned fishes, gradually transformed their fleshy fins into true limbs to navigate muddy swamps. But because they were ectotherms, meaning they relied on the sun rather than internal metabolism for warmth, they faced a massive hurdle. They had to figure out how to absorb enough heat to survive while simultaneously preventing their bodies from completely drying out in the open air. Now that we understand the basic timeline, you might wonder why this specific transition is so important to study today. The evolution of terrestrial ectotherms represents one of the most significant turning points in Earth's history. Without this successful leap from water to land, the vast diversity of terrestrial vertebrates, including reptiles, birds, mammals, and eventually humans, would simply never have existed. Furthermore, studying how these early animals solved problems like gravity and temperature regulation gives us vital insights into modern conservation biology. Today, ectotherms like frogs and lizards are highly sensitive to temperature shifts, so understanding their evolutionary constraints helps us protect them from modern climate change. Building on the importance of temperature regulation, let us look at the primary survival behavior these animals developed: basking. Basking is the act of lying in the sun to absorb thermal energy. For an early terrestrial ectotherm, managing body temperature was a matter of life and death. They could not just put on a jacket. Instead, their physical traits, like skin texture and body shape, interacted directly with environmental conditions to warm their cold blood. By understanding the physics behind basking, we can see exactly why early tetrapods evolved specific flattened body shapes to maximize their sun exposure and survive on land. To understand exactly how basking works, we can look at the convective heat transfer equation. Conceptually, this formula describes how fast heat moves from the warm environment into the cold animal. Let us break down the symbols. Q is the rate of heat transfer, measured in watts. The symbol H is the convective heat transfer coefficient, which accounts for wind and skin texture. A is the exposed surface area, in square meters. Finally, Tenv and T-body are the temperatures of the environment and the animal. Physically, if the exposed surface area A increases, or if the temperature difference is larger, the heat gain Q increases proportionally. This is why lizards flatten out on hot rocks. Now that we have our formula, let us see this with a concrete example. Imagine an early salamander-like creature crawling onto a sunlit rock. We are given an exposed surface area of 0.05 square meters, an environmental temperature of 30 degrees Celsius, a cold body temperature of 15 degrees Celsius, and a heat transfer coefficient of 10. We want to find the initial rate of heat gain. First, we calculate the temperature gradient by subtracting the body temperature from the environment, giving us a driving force of 15 degrees Celsius. Next, We multiply the coefficient, the surface area, and our temperature difference. The final answer is 7.5 watts. Physically, this means the animal absorbs 7.5 joules of heat energy every single second, allowing it to warm up rapidly for hunting. This rapid heating we just calculated leads us to an important question. If a large surface area is so great for getting warm, why aren't all ectotherms completely flat? The answer is water loss. While a large surface area helps with absorbing heat, it also exposes more skin to the dry air, causing rapid evaporation. This created a massive evolutionary trade-off for early terrestrial ectotherms. They had to balance the need to get warm enough to move and digest with the critical need to retain enough internal water to survive. To understand how they solved this, we need to look at the geometry of their bodies. To mathematically understand this evolutionary trade-off, we use the surface area to volume ratio. Conceptually, this ratio compares how much skin is exposed to the air versus how much water the body can hold inside. Let us look at the formula. We model the animal as a simple cube with side length L. The ratio R equals the surface area, SA, divided by the volume, V. Surface area is 6 times L squared, and volume is L cubed. In plain words, SA represents the skin catching the sun and losing water, while V represents the internal water reserves. Physically, if this ratio R is high, the animal has a lot of skin relative to its volume, meaning it is at a much higher risk of drying out. Before we move on to larger animals, let us calculate this ratio for a small early amphibian, which we will call animal 1. We are given a simplified side length of 1 meter. First, we calculate the surface area by squaring the side length and multiplying by 6, giving us 6 square meters of exposed skin. Next, we calculate the volume by cubing the side length, which gives us 1 cubic meter of internal space. Finally, we divide the surface area by the volume. The final answer is a ratio of 6. Physically, this means the small animal has 6 units of exposed skin for every 1 unit of internal volume. It will heat up incredibly fast, but it will also lose water at an alarming rate. Now that we have seen the danger for a small animal, let us prove why evolving a larger body size provided a massive survival advantage. We will set up our proof by looking at animal 2, which has double the side length, so L equals 2 meters. When we calculate the new surface area, we get 24 square meters. When we calculate the new volume, we get 8 cubic meters. The mathematical reasoning here is crucial. Notice how the volume grew much faster than the surface area. The volume cubed itself, growing by a factor of 8, while the surface area only squared itself, growing by a factor of 4. This sets the stage for a fundamental rule of geometry. Continuing our derivation, let us find the final ratio for this larger animal. We divide the new surface area of 24 by the new volume of 8, which gives us a ratio of 3. Now, we compare this to our first animal. The larger animal's ratio of 3 is exactly half of the smaller animal's ratio of 6. We have mathematically proven the square-cube law. The intuition here is beautiful. By simply growing larger, an animal naturally reduces its surface area relative to its volume. This evolutionary pressure explains why many early land-dwelling amphibians evolved to be quite large. A larger body size helped them retain internal water and hold on to their body heat much more effectively in the harsh terrestrial environment. Let us bring all these concepts together And look at this diagram of an early tetrapod. You are seeing a primitive amphibian resting on a muddy riverbank, actively basking. Notice the yellow arrows coming down from the sun? These represent the heat gain, or Q, that we calculated earlier, warming the animal's body. But simultaneously, look at the blue arrows rising from the skin. These represent evaporative water loss. The animal is caught in a constant tug-of-war between physics and biology. In the top right, the cube diagram reminds us of the surface area to volume ratio. By evolving a larger, thicker body, this creature minimizes those blue arrows of water loss while still catching enough yellow arrows of heat to survive. We have covered a tremendous amount of ground today. Let us review the key takeaways. First, the monumental transition from water to land forced early ectotherms to completely rethink how they managed their body temperature and internal water. Second, we learned that basking is not just lying around. It is a precise physical process governed by convective heat transfer, where surface area drives heat gain. Third, we proved that the square cube law created an evolutionary pressure for larger body sizes, allowing these animals to retain water while staying warm. You have now seen how the elegant mathematics of heat and geometry laid the foundational blueprint for all terrestrial life on Earth. Excellent work.